And exciting news for me, which means for all of us, is that we have an intern with us this semester. And I'd like to introduce Lance Meadow, who is with us from the university, but he's actually joining us from afar today because he's still on Christmas break or winter break. So Lance, I don't know if you want to unmute yourself and say hello real quick.
Hi, it's so nice to meet everyone. Thank you so much for having me. I'm really excited to help.
Good to have you aboard.
This young man is going to help us with all of the recordings and getting them properly uploaded to our YouTube channel, and he's going to be helping to co-host some of our courses. So I am deeply appreciative of ILR for this opportunity. Glad to have Lance with us. And I would like to go ahead and introduce John Axe this morning, who will introduce our speaker. And so let's have a great program. Thank you.
Thank you, Julianne. And again, Happy New Year and welcome back to the first lecture of the 2021 winter program. We're in for a real treat today. Dr. Fred Gregory is Professor Emeritus of History and Science and European History at the University of Florida. Let me give you a little bit of background. He holds a degree from Gordon Conwell Theological Seminary, a master's degree from the University of Wisconsin, and a PhD from Harvard University in the history of science. At UF, he has won both undergraduate and graduate teaching awards. And I have a copy of the 36 lecture DVD series from the teaching company Great Courses, which I have listened to and intend to revisit during the COVID lockdown. It's a wonderful series. This will be the 7th ILR lecture series given by Fred Gregory, dating back to a time before I even knew the ILR was in existence. But I've had the pleasure of hearing all of them starting in 2015 with the trial of Galileo, a 6-lecture series on fringe science, which was in 2017, a 4-lecture series on voyages of discovery in 2019. He's one of a few special people who, when he finishes one series, the first thing we ask him is, when can you come back and what would you like to talk about? So please welcome with a Zoom thumbs up, Professor Frederick Gregory. Take it over, Fred.
Thank you, John. I guess everybody can hear okay, huh? Thanks. Well, it's a great privilege for me to be back. I always enjoy, and I see a lot of names that I know, people that I've come to know over the years, and I always enjoy being together with seniors who are intellectually curious, and that's what you have at Oakhammock. So I congratulate you on the success of the ILR. What I have for you today, I will now start sharing the screen. It'll take just a second. And I have to, now we've properly scared you, I hope. So this is what we're going to be doing for the next 6 lectures, Science and Culture in the Nuclear Age. I'm going to give you a reprise of the lectures. Today, we're going to talk about astounding revolutions in nature, writ, small and large, or large and small. That's today's. And then next time, we're going to be talking about why splitting the atom was impossible. And then we're going to talk about the horrifying prospect of thermonuclear bombs, the H-bomb. And then we're going to go more into the cultural aspect of things, the nuclear holocaust in literature and film, and I'm going to remind a lot of you of things that you've seen in your past, like Dr. Strangelove and also literature. Then we're going to look at whether or not the political scene is capable of containing the threat to life on Earth. We're going to review, of course, the Cuban Missile Crisis and the SALT I and II talks and that kind of thing. And Then we're going to end with weighing nuclear accidents. And we're going to have a general discussion. The last session I see as more of a general discussion, and I'm going to draw on some expertise that resides with you guys on this, because we're going to look at 3 Mile Island and Chernobyl, of course, but then we're going to try and ask questions, which we will explore together about how we're going to do this in the future. And so that's what the scope of the lecture series will be about. But today we're going to be talking about these astounding revolutions, and I'll tell you what those are in a second. But I should preface it by also indicating that this one was an assignment that I was given when I was asked about teaching a course, and I said, well, what do you think about exploring the nuclear age? And John, of course, was very amenable to that. And then he asked, I guess the committee made the request that I deal with 2 revolutions of the 19th century that predate the development of nuclear science. One, of course, is relativity, and the other is quantum mechanics. And I said, oh, well, thank you for an easy assignment. In one lecture to do that, you'll see is going to be not in great depth, but probably a little bit more in depth than some of you would care. So it may be a little more sciencey today than cultural, but we'll we'll do our best at taking on this assignment. So the first revolution, excuse me, relativity, altered our understanding of space and time, while the second one overturned our assumptions about the behavior of energy. Now, I want to request that you keep your eye on what the basic message will be from these lectures. Obviously, we're not going to become experts in either relativity or quantum mechanics or quantum theory. I'm going to try and give you some sense of where these things came from and what the basic issues are that they evoke, all right? And then we're going to be satisfied with that, because both challenged our common sense and intuition about nature. And we'll see that that is very clear. It was not something that the 19th century was prepared for. The 19th century was a century that had great success in science. And so they had the idea that things were kind of wrapping up. Here's what Mendenhall said. I'm going to have to be careful here. Just a second, I have to adjust my screen so that I can see the whole thing. Yeah, I had your pictures were in the way of half of it. All right. So in AAAS, American Association for the Advancement of Science, president said in 1887, more than ever before in the history of science and invention, it is now safe to say what is possible and what is impossible. No one would say for a moment that during the next 500 years, the accumulated stock of knowledge of geography will increase as it has during the last 500. In the same way, it may safely be affirmed that in electricity in the past 100 years, will not like to duplicate in the next, at least as to great, original, and far-reaching discoveries. And this is from Albert Michelson some 7 years later. He was one of the authors of the Michelson-Morley experiment. While it is never safe to affirm that the future of physical science has no marvels in store, even more astonishing than those of the past, it seems probable that most of the grand underlying principles have been firmly established. It is here that the science of measurement shows its importance. An eminent physicist, everybody thinks that's Kelvin, and it might have been, an eminent physicist has remarked that the future truths of physical science are to be looked for in the 6th place of decimals. In other words, we've got it down pretty well. We do have to clean it up to maybe the 6th and 7th decimal point, right? And this was on the eve of both relativity and quantum mechanics, which were exactly what he said we wouldn't have, great and fundamental new discoveries that change our way of thinking. The first we'll talk about is relativity, and the individual that we always associate with that development is, of course, Albert Einstein. And as a kid, he had read a series of books that a friend of the family had given him. They were by a Reform Jew in the middle of the 19th century. Reform movement in Judaism was just really getting well underway. And this individual was an editor and also had put out this multi-volume series of books. Basically, they were called natural science, popular natural science for the people. Well, actually, the title in German is a long one. I won't give you it, but I did a talk once at up in Massachusetts on this book, or on this series of books, and Einstein's interaction with them. And it became clear that they were probably written for kids because of the way in which they were written. They're very didactic, and the author kind of takes you by the hand and leads you through a lot of scientific issues. And it's from this book, among other things, that Einstein developed what I'm calling a religious outlook. And by that I mean a belief that nature is harmonious, that it's rational and it's uniform and it's going to be consistent, right? In the course of his life, he would encounter two major challenges to this religion, and they are the topics of our talk today. The first one, relativity, as we know, he overcame and solved that one. The second one, he didn't. So we're going to get a look at that. Well, the first one, relativity, had a challenge in it that was due to Galileo and his concept of inertial motion. Galileo had declared that rest and uniform motion were equivalent states of being. That is to say, they're both the same state of being. He had used this to explain why the Earth could be moving around the sun and we not feel it. So I'll unpack that a little bit. For example, we all accept that when you go on a cruise and you want to play ping pong on a ship that's moving smoothly, it has to be moving uniformly. It's just like it was at rest at the dock. You can play the ping pong game, no problem whatsoever. So what Einstein would point out, that is, if you don't have any indication of a different frame of reference, if you're in a windowless room that's moving uniformly, you do not know if you're moving or at rest. There's no way of telling. You could be neither. In fact, as we speak, we feel like we're at rest. We're actually moving, of course, around the center of the Earth's axis. We're going around the sun. The sun is moving in the galaxy, and the galaxies are expanding. So we're going in multi-directions at the same time, and we don't have a sense of that because we don't have reference outside of our own system here, except we know the sun is moving relative to us because we can see it. There's a different frame of reference. Well, Einstein expressed this equivalence of rest and motion this way. The laws of physics are the same for all observers in uniform motion. So if you're moving smoothly or you're at rest, the laws of physics will be the same. Now, in one of the books of that series that I mentioned, as a teenager, Einstein ran across the idea of riding on a beam of light. What that author did was to use he wanted to do a tour of the planets, right? And so he was taking kids, I'm assuming it was written for children, wanted to take them on a tour of the solar system. So he said, well, how shall we go? Well, we can't go by horse and carriage. It would take us forever to tour the planets. We can't even go by these newfangled locomotives that we see that go these incredible speeds, 30, 40 miles an hour. We'd never get there, even at that speed. But if we could ride on a beam of light, we could get there quickly. And Einstein ran across this idea of riding on a beam of light as a teenager, and he exploited it later. The more he considered what the world would look like if he could ride on a beam of light, the more he realized that even imagining doing this, exposed a case that challenged his religion. That is, that suggested, well, there's this problem with nature. It doesn't seem to be consistent. So I'm going to try and unpack that for you. Now, remember what his religion was again. It's that the universe is rational and uniform. How did this riding on the edge of a beam of light challenge nature's uniformity? Well, it did so by presenting a case that appeared to be an exception to Galileo's claim that the laws of physics are the same for all observers in uniform motion. That had become such a cardinal axiom of physics that Einstein was very reluctant to give it up. But this one case that we're about to look at challenged it. And how did it do that? Well, what if the little guy could figure out a way to tell whether he was moving or not? Because remember, if he's riding on the edge of a beam of light, in front of him is nothing but blackness, right? So he has no reference to anything. he should not be able to tell whether he's moving or at rest because he has no way of getting to another reference frame. So Einstein said, let's do a thought experiment. Imagine that the little guy is riding on the leading edge of a beam of light. So in front of him is complete blackness. We're going to remove the objection some of you are thinking about right now. No, he did not turn around and look backwards. I can't allow him to do that or it would ruin everything. So we'll agree that he didn't do that. So he can't tell whether he's moving or not. Now remember, light moves uniformly, so he can't tell. Einstein asked himself, if this little guy held a mirror in front of him, would he see his reflection? Well, that's an interesting question because he's riding on the edge of the beam of light. So if he held a mirror out in front of him, it would be in front of the light. So no, he wouldn't be able to see that reflection because the beam on which he's riding can't catch up to the mirror to be reflected, right? Because the mirror is going the same speed if it's going but if that's so, he couldn't be at rest because if he were at rest, the light would go on ahead of him and be reflected. So you see the problem he has. Wait a minute. So if I held this mirror and I didn't see my reflection, then that would mean that, everything was as it should be. But if he were at rest, he would see the reflection. So what to do? So he must be moving because he can't be at rest or he'd see the reflection. But he shouldn't see the reflection or there's something screwy going on. So Galileo's relative motion says you can't tell if you're moving or not from within your reference frame. So now Einstein has a contradiction. So what can he do? Well, he has two choices. He can abandon his belief in the harmony and universality of nature's laws by conceding that in at least one case, the laws of physics are not the same for observers in uniform motion. In that case, the mirror would remain dark. Or he could insist that the laws of motion are the same for all observers in uniform motion, including the observer riding on a beam of light. Then the mirror would show his reflection. Well, what do you think he did? He said, since he'd see his reflection if he were at rest, he would also see it here. In other words, rest and motion are supposed to be identical states of being according to Galileo's reference frame, and he did not want to give up that. So he just said, I would see my reflection, even though that doesn't make any sense. But then how does the light get ahead of the little guy? It just does. That's the answer to that. That no matter how you measure the speed of light, whether you're moving or not, whether you're going with it or against it, it's always going to come out the same. That's not intuitive. If you're riding on a train and you roll an orange down the aisle of the train to somebody else up ahead of you, it would depend on how an observer outside the train would see whether or not that you were going with the motion of the train. If you're going with it, the observer on the outside of the train would see it to be going the speed of the train plus the speed of the roll. And if the train were going against that, then you would, against that roll, then you would see the difference between, in other words, the speed of the train minus the speed that you're rolling it. So it would matter which way you're going. Not if it were behaving like relative motion, in this case does, you would get the same in any case. That's only when you're dealing with light, Einstein said. It's an exception. Well, he stuck to his religion and insisted that the laws of physics are the same for observers at rest or in motion at a constant speed. And since at rest we would clearly see our reflection, we must also see it if we're moving uniformly. So there are consequences for being so dogmatic. He was saying that the speed of light is constant regardless of how it was measured. If velocity of the light is constant, then space and time have to change together in order to accommodate the conclusion that light is not like other things. So velocity is distance over unit time. So if my velocity is going to always be the same, then d and t have to change together. Like if your velocity is 4, well, you could be going 4 miles. Let's see, if velocity is 2, let's say, then you could be going 4 miles in 2 seconds, or you could be going 8 miles in 4 seconds. But at any rate, d and t have to change together in order to keep that v the same. So that's one of the consequences, that space and time have to change simultaneously if we're going to insist that this is the case. So his new system was very hard to swallow for most, but it possessed a conceptual and mathematical elegance that was tempting. But to many, it seemed more philosophy than science, and it was unproven. But Einstein persisted, and he announced this in 1905, and it's become known as his theory of special relativity. And the reason it's called special is because he was insisting that you're dealing with motion at a uniform velocity. Now, if you're talking about motion at a uniform velocity, one of those velocities could be zero. That's the case of rest. And then it doesn't matter what any other uniform speed is, as long as you keep it uniform, then that consequences that I've been talking about pertain. So this is a special theory of relativity because you're requiring the motion to be uniform. But a decade later, he was able to generalize his conclusions. In other words, he said to himself, well, wait a minute here now. This is nice for things that, frames of reference that happen to be moving uniformly with each other, with respect to each other, but that's probably not that likely. In other words, most reference frames in the universe wouldn't be confined to moving uniformly. So we got to become more general than allow motion to just be uniform. And so he later was able to conclude the general theory of relativity about a decade later, in which he claimed that the laws of physics are the same for all observers. Well, that received some experimental confirmation in 1919 from observations made during a solar eclipse, because during a solar eclipse, the stars near the sun are visible when they're not visible, of course, if the sun is shining at all. So you can see some of the stars right near the sun during a solar eclipse. Pardon me. So what that made possible was to see whether or not another implication of the general theory was that light would bend in the presence of a large mass. Well, you could see then whether that light from the stars nearby the sun in the background there, which would have to pass close to the mass of the sun, whether they were bent, and they were. And so that proved the general theory in the minds of most people. All right, so we have dispensed with relativity, I hope, but you probably have some questions and we can deal with those a little bit later. The second challenge to Einstein's religion was much more lethal. It has to do with quantum theory, which produces paradoxes of its own. And they fundamentally challenge nature's rationality too. So you can imagine that Einstein's going to have problems with this because he believed that nature was rational and uniform. That was what I'm calling his religion. He gets it from Plato, I'm sure. Nature presents itself to the world of the atom in a manner that escapes normal mechanistic analysis and relies on probability. So we'll get into that a little bit here as we go. You've heard all these famous quotations from Einstein. God does not play dice with the universe. God may be subtle, but he is not malicious, meaning that God would never create a universe that was not rational. That was his belief. Bohr got tired of that, hearing that from Einstein. And at one point, Niels Bohr said to him, stop telling God what to do. In other words, you're telling God that he has to create a universe in a certain way. You don't have the right to do that. They used to talk about things like, and that's the context in which Einstein talks about religion a lot. You get a sense of why I'm calling it his religion, because he always uses God to stand in for the rationality of the universe. So when we talk about quantum theory here, we're going to go from the universe writ large, which is relativity, that is planets and galaxies, to the world of nature writ small, atoms and nuclei. It's the study of light, which is electromagnetic radiation, after all, at the end of the 19th century that we're going to focus on. And it went down three paths. The first one was the Earth's motion through the ether. That leads to relativity. That's another way to approach the study of relativity, to talk about Michelson-Morley and all of that. I didn't do that today, but at any rate, you can take it. This is one of the ways in which the study of electronic radiation led to relativity. The second is that the distribution of light energies that are sent out by different sources. I'll explain that in a bit. That leads to quantum theory. The third one is the radiation, X-rays, radioactivity, that lead to nuclear physics and elementary particles. Today, we're going to be talking about that second one, the distribution of light energies that are sent out by different sources. So I'm going to be oversimplifying this a lot in quantum theory. Why? Because it can easily get extremely technical. But the most important reason is I'm not a physicist, so I can't really explain all of the intricacies of my quantum theory. And I'm hoping that you aren't able to do that either. Although if some of you have an expertise in this area and want to chime in at the end and point out things, I'd be happy to have you do that. So what is the distribution of light energies from different sources all about? First of all, why did I put light in quotation marks? Because what we normally mean by light is visible light, and that's just part of a larger picture. Here's the electromagnetic spectrum, and I'm trusting you can see my cursor here. It goes from long waves, radio waves, microwaves, infrared waves. Just below the visible is the infrared. And this visible light is just a short octave or two. And then we get into ultraviolet, we get into X-rays, and then these are all short waves. These are longer waves. These are high frequencies. These are low frequencies. So when you get over in here, you're getting very short rays, high frequency, short waves. Gamma waves are even, and if you wanted to, you could go off this chart here and you'd get to the electron, which is so focused that we argue about whether it's a particle or a wave. So you can see then that we're going from increasing energy. These are relatively low energy because they have long waves, but they're very low frequency. Over here, they're very short waves, but at high frequency. So you can imagine they are going to produce more energy when they're radiated. Now, everybody knows that as the temperature of a body is increased, it radiates heat. You see it often as a dull red glow on the burner of your stove, for example. And then if you really continue to heat it, you can even show it as white heat. At an even higher temperature, it gives radiation in the invisible range of X-rays and such, ultraviolet rays. As the 19th century drew to a close, several physicists were trying to understand a general relationship between temperature and radiation. So you see the same temptation for them here that you saw with Einstein. He did get a result for the special theory when he confined his attention to frames of reference that are moving uniformly with respect to each other. But then he said, yeah, but nature's not going to be confined to that. We need to be more general and allow frames of reference to move accelerating with respect to each other. Well, here, they wanted to get a general formula that would express the relationship between temperature, radiation, and energy. Now, the model of radiation they were working with presented a major problem. Well, what was that model, and how did they envision what caused radiation? Well, they had what they called the resonator model, and this was imagining that in the walls of a substance that was being heated, there are vibrating electrical charges. They could have been thinking of the new electron, which had just come into being in the 1890s and after the turn of the century. But you can see that vibrating electric charges might do it, because if you have a vibrating electric charge, that's actually a changing electric field. And what they had learned in the 19th century was, if you have a changing electric field, that produces a changing magnetic field. But a changing magnetic field also produces a changing electric field. So they keep producing each other, and that's an electromagnetic wave of radiation. So as a charged particle vibrates by moving up and down or back and forth, it produces changing electric and magnetic fields that move away from the vibrating charge in many directions. So as you can see here, the energy that's given off by the various kinds of radiation should increase as you go from the low frequency, long wavelengths to the high frequency, short wavelengths. This is increasing energy, and it should increase as you go from infrared toward the ultraviolet. But recent experimental results were incompatible with this model. I mean, the model was helping them a lot to get a handle on this general question, but there were some results that weren't really helping. Lord Rayleigh and James Jeans collaborated and came up with a graph that captured their experimental results for the infrared region, that is the low the low, long wavelength, low frequency in the infrared region. And this was the curve that they came up with. I'm going to tell you something about that curve. It's not really a smooth curve. We'll tell you about that in a second. But they did capture that, but they couldn't do anything with the stuff over in here. That just wouldn't, they weren't working on that part. Well, somebody else did, though. A guy named Wilhelm Wien came up with a curve for the ultraviolet end. You can see that it is going from here down here. Now, you might already see the problem. The problem is that over here you've got high energy, but they're showing that the amount of energy is decreasing in what they call the ultraviolet part of the electromagnetic spectrum. So that was an enigma. The resonator model suggests that the energy should increase rapidly in the high frequency area over in the ultraviolet, since the vibrations there would be much faster. So you would think that the amount of energy would be going off. And in fact, they were saying it should go off, according to our model, to infinity, really. And that was called the ultraviolet catastrophe of this model. Namely, that in the ultraviolet region, you should be getting this incredible amount of energy in the radiation, but it wasn't. It was going down. So how in the world can you deal with that? There was another physicist who was trying to solve the problems of energy distribution, and that was Max Planck, whose name you probably have heard. Planck was old school. Now, by that I mean he wanted to find what he called the absolute law, which would be a smooth curve that would say exactly how nature worked. It would incorporate what Rayleigh-Jeans had done and what Wien had done. It would cover the whole range of the spectrum and not leave out the middle range there that these two other experimental physicists had come up with. The problem was that no matter how hard he tried, he could not find a curve that worked. Now, there was another guy, another approach out there dealing with questions of thermodynamics, and that was Ludwig Boltzmann. I got a picture of Boltzmann there, and I didn't realize there was a GIF attached to his beard, but that's just thrown in for extra. You don't have to pay for that. That's just bonus. Boltzmann's approach was statistical and probabilistic. He wasn't after a smooth curve that would capture the absolute law. He didn't care about that. He wanted a statistical law that was just fine for him, even though it was only saying how nature was most likely to behave. Well, that wouldn't satisfy Planck. Planck was old school, like I said. He believed that nature was rational. You should be able to capture it. No questions asked about dice or anything like that. Finally, out of desperation, Planck gave in and turned to Boltzmann's approach himself when he failed to get it any other way. Now, if he's going to use a probabilistic approach, he's going to have to find something to count. He decided he could use what are called differential pieces, which if you've had calculus, you know what I'm talking about, but if you haven't, I will show you pictures of what they look like. Rayleigh-Jeans and Wien had employed these in expressing their results. So even though they looked like smooth curves, as I said, they weren't really. In the Rayleigh-Jeans formula, for example, which you see indicated there, and I don't ask that you understand what that all means, but it gives the energy per unit wavelength. This kind of equation is called a differential equation, and these things here are called differentials, right? Each one of them. So what is this unit wavelength? It's this thing right here. It's called du, nu, actually, that's the Greek letter nu, which was used for frequency back in the day. And so what is that all about? Well, mathematicians had long ago, under actually close to Newton's time, figured out a way of getting the exact area under a curved line by using rectangles. And that's called approaching, this is one of the first problems you'll do in calculus, is to figure out how you solve that. What they do is they put rectangles, they inscribe, or in this case, they circumscribe rectangles around the curve that they're trying to calculate the area under. And you can see that the sum of those rectangles, if you can do the area of a rectangle real easy. And you can see that if you add them all up, you'd get an approximation of the area under that curve, but it wouldn't be exact. So what they do is they prove there's a limit toward which these approximations are going. The limit then, if they can show that it exists, would be the exact area under the curve. This is a process known as integration, which is usually what follows after you study derivatives, you study integrals in calculus. And the process of integration does this. It shows you how to calculate the limit of a sum. So these sums then, they allow those rectangles to get much more numerous, and then they allow them to go to infinity, and they can get the exact area. Well, by using Boltzmann's approach and taking the best from Rayleigh Jeans and Wien, Planck finally found a graph for the whole spectrum. But remember, these curves here, all of them, because Rayleigh Jeans, I've already showed you what the pieces were like. It's like there were little rectangles there, and they're using those in place of the smooth curve, right? They involve differential pieces of the dependent variable. So this is the way it would be. I didn't have the patience to do all of them under Planck's curve, right? In other words, Planck had, you could do all of them, but that takes a lot of PowerPoint work. And I thought you'd be satisfied with this little portion of that curve that Planck was trying to come up with, this one here. He was trying to do the last step, which you do when you have a differential equation. You integrate it and get a smooth curve. But whenever he did that, whenever he tried to solve that differential equation that would apply to the whole thing, the area in here would go screwy, and it wouldn't make any sense at all. It would be all over the map. So he couldn't do it. And so he didn't know what to do. Every time he tried, the middle range of wavelengths went screwy. He finally threw up his hands and just said, well, I'm going to have to be satisfied and leave this in differential form, as if there are pieces of rectangles in here. And I said, he's old school. He doesn't want to do that because that's too unfinished. He wants the exact area under the curve, and those pieces are not going to give him that. And so he wasn't happy about it, but he didn't know what else to do. So he finally said, well, we can use this data. It won't be exact, but we can use it. He didn't claim that his result meant that nature itself was not in fact smooth. He didn't really say much about that at all. But he did present a formula for calculating the energy of a differential piece. It's E equals h nu, where h, without units, is a very small number. It's become known as Planck's constant. And this is the Greek letter nu. So energy equals h times the frequency, really, is what he's saying. In other words, the frequency for a given rectangle. So what he's saying is that if you were going to claim that this is the way nature really is, you would be saying that nature is not smooth, but jerky. It's more like eggs and not milk, by which I mean, if your mother sends you out to the store to get some eggs, she's not going to expect you'll come back with 1.3259 eggs. You could come back with that many quarts, 1.325, because measuring milk is continuous, right? But eggs are not that way. And what he's saying is nature is more like eggs than it is milk, if you insist on applying that formula and saying, well, that differential equation is really the way nature is. When energy is given off or taken on, if you are saying that nature is really that way, it does so in bullets or packets. In other words, there's just little eggs of nature, if you will, or energy, I mean. So Planck's formula gives you the energy of a packet. Planck's idea about energy did solve the ultraviolet catastrophe, which was a wonderful thing because, well, what was that problem? It suggested that at high frequency, over in here, the energy would increase without bound. That was called the ultraviolet catastrophe. And the problem was, of course, the experimental results showed that it decreased. Well, how could that be? Well, Planck was able to say, if these results, like Wien's and Rayleigh Jeans before, then you would be able to kind of approximate this curve. It's not really smooth. If you could take a microscope, you would see these rectangles in there, but they're so tiny that you can't distinguish them when they're platted alongside each other, and it looks like a smooth curve when you put the curve, I've got it here inscribed, but if you did it superscribed, it would be the same thing. So you can imagine, here's how we can solve the ultraviolet catastrophe. You could imagine that nature might be such in this radiation that we're trying to deal with, that you have a lot of these relatively low energy packets, because remember, the energy, any one of them, is Planck's constant times the frequency. Well, this is a low frequency. But if you have a lot of packets, which I'm indicating by the width of this rectangle, then you would get this much energy over here, all right? Whereas if you were over here in the high frequency area, and remember, he could get this solved as long as he did it with rectangles, then the energy of a given one would be high. But if there weren't very many of them, then you would only get, you total them all up and you only get this much. So it could be, there is a conception that says, well, it might be that we have different amounts of these rectangles, so to speak, so that over here in the infrared region, we get more energy out of them than we do over here, or at least explain why this is coming down as opposed to going to infinity. Well, if quantizing energy were only useful in this specific context, it would never have become so fundamental to physics. I mean, that would be nice, but, you know, it's asking a lot. It's like Galileo, you know, yeah, I can solve this problem as to why we don't feel motion. It's because there's a kind of motion that's equivalent to rest. And you can imagine the critiques, the Aristotelians saying, right, I'm going to give up Aristotelian physics so you can do that and solve your problem. Not an idea I'm going to get behind. Well, that's what a lot of people might have thought. Yeah, this solves the ultraviolet catastrophe, but that's not enough to make me change my mind about the way energy is given off or taken on. So it was long before the idea of quantized energy began to explain problems in other areas. One was the so-called photoelectric effect that Einstein did. And that is, if you shine light on certain metals, you can get it to produce electric current. In other words, you can get them, the energy of the light coming in is going to knock some electrons off, but only in certain cases. So how could the energy in the wave knock out electrons? And why did shining brighter light not produce greater current? That was one of the enigmas of the photoelectric effect. I got a bright light and it doesn't produce any more current than a lower intensity light. However, if you change the color of the light, you can get different amounts of electricity being given off. Red light, for example, you can't get any current out of that. But if you use blue, you could. So how to do that? Well, here's an idea that Planck could help with. That's energy is equal to the Planck constant times the frequency. I've used F here. This could make sense. Why? Well, you got different frequencies for blue light. It's a higher frequency, higher energy piece. So when you shine blue light, it has more energy and knocks the electrons out. But if you shine red light, it doesn't have enough energy to knock out the electrons, no matter how many you put in there. All right. So you have to have high energy packets of energy in order to get that out. So that explained it. And that was assuming that energy was quantized, that it given off or taken on in packets. So that was something that seemed impossible, right? Because what does it mean to suggest that we must treat nature as if it's jerky and not smooth? Well, it means that if you're going from 0 to 10 miles an hour in your car, that you're not going all of the velocities in between. You're starting at 0. You're not going to a continuous next value. You're jumping up to the next value. You've got an egg's worth. So if you went from 0 to, let's say, 1 mile an hour, I'm making that jump huge, then you were never at half a mile an hour. It's almost like you were disappearing at 0 and reappearing at a half mile an hour on your way up to 1, right? That's what nature being jerky would mean. And that didn't make any sense to anybody. It seemed to be not only, counterintuitive, but it was probabilistic. It was not something that somebody like Einstein would like to see, who wanted to believe in an absolute law like Planck. He wanted to not have probabilities, but he wanted there to be an exactness about laws that did not have any iffiness about them. And so this was a case where the impossible turns out to be, if not possible, at least it helps us solve problems. And what more can you ask of a scientist than to come up with something that solves the problems, even if the implication about the way nature, quote, really is bizarre, all right? And that's That's what it was when quantum theory began to settle in, which wouldn't be for a while, because these results here would take some time to be grasped by everybody. And then you'd have to have some more things happen before people would begin to conclude, yeah, maybe we just have to live with this contradiction of things. So next time we're going to look at another impossibility, the splitting of the atom, because that was seen to be, well, you can't do that. After all, the atom is the uncuttable. That's what it means, right? So I'm going to stop sharing now and come back. Hey, you're still awake. Great. So I'm wide open to questions, and I realize this has been fast and furious here, but we do have some time for some questions and comments. I'd be happy to have those of you who have background in these things to add it. But what I want you to get out of this, what do I want you to get? I want you to get that sometimes science presents us with things that seem bizarre and that we're not ready for. And you can see why it's going to be almost inevitable down the road that somebody's going to come along and start summarizing this kind of phenomenon with a question of a paradigm that shifts. You know, that's going to happen, right? And of course it does with Kuhn in 1962. But so the important thing to keep your eye on, what are we learning from this? Well, I hope you have a little bit of an idea of where relativity came from, what Einstein was trying to do when he got it. And then he was able to make a solution to that kept his idea about nature's rationality for him, as long as he just said light is special and it doesn't behave like other things, but this is an implication of it, space and time have to change. But if you want to be consistent, then that's what you're going to have to do. And then with quantum theory, this is totally impossible. And we weren't expecting it, as the quotations from the end of the 19th century show, but science can all of a sudden turn things upside down, and you just have to get used to a new reality. So keep your mind open, I guess, is the lesson there. All right, I'll stop. And John, you want to, I don't know if there's chat questions. I'm not good at paying attention to chat while I'm lecturing. So if somebody wants to tell me what they're in there, I'll be glad
That's
to.
okay. That's why I'm here to help.
Okay,
John
great.
Axe, if you want to make any comments before we start calling on questions.
No, I'll make some comments later on, but I'd like to first take questions from the rest of the audience.
Okay, go ahead, Richard Petway.
Okay, I have one that is a mystery to me that you could probably explain. For example, I've heard that and I've seen that if you heat a metal to a high temperature, the metal that was formerly had magnetism, the magnetism goes away. And I don't understand how when you heat a metal up to higher temperature, it loses its magnetism. Does it? Because it seemed like inducing heat to waves would not make it necessarily go away. But they use this in determining the temper quality of steel. Is that as they heat up the steel before tempering it, it loses its magnetism, and I didn't understand the relationship between heat and magnetism in metals.
Well, Richard, you've exceeded my ability to answer that question. I can guess one, but I don't have any confidence in it. There are some physicists here. Maybe John can speak to this, but I would guess that at the really high end of the spectrum, with high temperatures, great amounts of energy, that the expression of the electromagnetic connection, which had been uncovered by Ørsted back in the 1820s, would change somehow. And that doesn't answer your question. That's just kind of begging off. But if there's anybody who does have an idea, that'd be an interesting thing to learn. I'd also like to know that.
I will take a crack at giving Richard some ideas of what you're talking about. Is a phase transformation, a transformation between a state in which a metal is magnetic and one that isn't. That's just one example of a phase transformation. Another simple kind of a phase transformation, take water. Water at high temperatures is a gas, it's steam. You cool it down and it becomes a liquid. You cool it down further and it becomes ice. So the amount of energy that the individual molecules of water have determine whether the composite is a gas, a liquid, or a solid. It's the same, that's the same thing with a chunk of iron. Each individual atom in the chunk of iron has magnetism, but whether the magnetism chooses to be pointed random directions or pointed in a single direction is determined by the amount of thermal energy that's in there. So it's a very it's a special a special manifestation of a very wide known effect of how thermal increasing the thermal energy in a material can cause it to change.
But is there a standard relationship to between temperature and before the shift? In other words, is it could you graph that function of heat versus magnetism or changes in composition? Is it linear? Is it become exponential, or what is the relationship between heat and magnetism and metal?
Well, yes, magnets have been studied a lot because there is particularly simple to make a theory which explains the behavior of the magnetism versus temperature, and that's because you're dealing with only one element of the kind of different things that iron has, and that maybe is its magnetic moment. But yes, it's you can do similar things with other kind of phase transformations as well.
Okay, Eli?
Yeah. So I hope my question isn't too esoteric. Can you hear me?
Yep.
Yeah, okay. The thing that makes us human is our ability to take phenomenon that we can think about, like Einstein's visualization, his thought experiment. It's kind of a human thing for him to do. But the thing that makes us human, as I thought from what I read, is our ability to make models, to create abstract ideas. For example, mathematics is a model. It takes the nature that we experience and that we think about, and it converts it into something which is a model of the phenomenon. For example, we talked about magnetism and electricity, and Maxwell's equations describe very precisely that. And as far as quantum effects, and I understand Maxwell's equation, but it goes far beyond me, maybe many of us, to understand Schrodinger's equations, which begin to explain the quantum stuff. Do you have any sense of what these guys did in being able to go and use the concept of creating models for their stuff in a mathematical form? Is there any way of explaining that?
Yeah, I think there's some things that can be said. Of course, when you're trying to talk about how geniuses do things, we're all being presumptuous, and these guys are unusual people. Let's take Maxwell for an example, and may be able to answer your question that way. Maxwell was an Englishman, right? So he's very practical. Actually, he's a Scot, So even more practical, maybe. And so that's not irrelevant to his model. The 19th century saw nature mostly as a machinery. Right there, you've already got a model, right? You're saying that nature behaves like a machine does. We can take it apart. And Maxwell was completely devoted to this approach. When he was a kid, he would take toys apart, his parents said, and they asked him why, and he said, I want to see the go of it. And so he thought that if I can understand how these parts interact, I can understand it. That's what understanding is. So when you look at Maxwell's model, what he did was to envision the electrical effects, because as I indicated earlier, Ørsted and Faraday had developed this notion of electrical relationship with magnetism, electromagnetism, right? And when he thought about that, he thought about it in mechanical terms. And he decided that he would imagine the ether, which was real to him. The ether is a very nebulous, extremely nebulous, well, it's an ether, right? So it's not like regular matter, but it exists. And he gave it a twist. And then I can describe a twist in the ether mathematically. So he wrote an equation that does that. And then he also allowed there to be little ball bearings. Now you see the mechanical part coming up. To between these little twists were like little entities, and he put little ball bearings between the entities, and they all moved together. So when one moved, they all moved. And by allowing one of the aspects to express electrical phenomena and the other to express magnetic, he was able to make a set of equations that captured that all together in one set, right? What the Frenchmen did when they're not as commercially minded as the English. They've always been the theoreticians, right? And what was it Legrand said about when he became blind? Good, then I won't have diagrams to distract me from thinking really mathematically, right? Well, not so the English. They loved these model making business. And so what Maxwell was able to show then was how you move one of these parts with respect to the other by twisting it and then allowing that twist to roll on rollers. And you can express this whole thing about electricity and magnetism's relation to each other. Not only so, but in the process of doing it, you notice that there is a constant that emerges. And lo and behold, when you calculate what that constant is, it's the speed of light. And that allows him to conclude that electromagnetism has something to do with light, that light is electromagnetic radiation, right? So it was very fruitful to do this. But when the French saw it, they said, we thought we were entering the abode of reason and we find ourselves in a factory, for heaven's sakes. You know, they just thought that was terrible. But it illustrates your point that we come up with models from various ways, from various sources, and they turn out to be useful, and it surprises us to some extent. I have one more comment and then I'll stop. But the other thing that your remarks stimulated in me with the notion that what we're doing when we're making models is we are expressing the way our minds work. This is our minds being confronted with a reality that's different from us, right? And so we're trying to make sense out of that. And we know we're not free to just say anything. And so we try what the best thing we can come up with, but we're just utilizing tools we have. Where do those tools come from? Well, they come from our culture, from the time we are born, you know, the time in history that we are in, that at certain times there would be, you know, different possibilities. There's a bunch of scholars who've done a lot of research on why Darwin's theory comes about in a time of economic expansion and mutual competition, right? That's an English thing, and it's not only English, but it's all over the place. The societies are becoming more industrial, etc. So this way of thinking is much more, you're reminded of it everywhere you look. So why not have it used in science? It's a competitive thing out there, you know, whatever. And so those, the very precise scientific theories reflect the larger culture. And so, you know, sometimes that surprises us, but when you stop and think about it, we are in the last analysis what Kant called lawgivers. We impose these things on nature. And nature sometimes laughs at us, as it does in quantum theory, and saying, Nice try, guys. It doesn't work. It's not rational.
Thank you. Rick Gold?
Thanks so much for the lecture. I know that you were simplifying when you talked about Einstein's religion of having faith in laws of the constant laws of nature. Einstein was a strong follower of the Jewish renegade philosopher Spinoza, who was pretty much a pantheist, who said that God is nature. I was wondering if you had some other things that you might comment on how Spinoza contributed to Einstein's thinking.
Yeah, I think it's very, Einstein's religion, as I've called it, is very Spinoza-like, very much. Spinoza, as you know from perhaps your own research and reading, was, as you indicate, a pantheist. He concluded that all of reality, and now when he says nature, he includes mind in that. Mind is part of nature. So for Spinoza, matter and mind are not, they're two sides maybe of the same thing. They're not separate entities the way that we tend to think about them in the wake of Descartes, who wanted them to be cleanly separated, right? It's all one thing, and it's monistic, it's not dualistic. And so that's definitely the way Einstein approached things. It is not very orthodox in a traditionally religious sense, but he is fond of talking about God all the time. So Spinoza was very influential not only on Einstein, but much earlier on a number of thinkers, in particular the German natural philosophers. They were called nature philosophers, Naturphilosophen, who were very romantic in their approach to nature and did have a way of insisting that mind and matter are one thing. You can't, when you separate them out, you distort something, right? You distort the whole. And that was influential and noted in continuing this idea that you can insist on rationality through that the ideal is actually the real. And there's a consistency there that you get out of that. And I've argued in some of my research that this was an echo that went down through the 19th century and continues to our own time. So yes, I think Einstein was definitely influenced by Spinoza.
I might say just a couple of words about Einstein. People have the impression that Einstein was a great mathematician. He was not a mathematician at all. He said something to the effect, "I have no special talents. I'm merely curious." And what motivated him were what he called these Gedanken experiments. What would happen if I was riding on a beam of light? And he tried to take the simplest case and understand it. And he was very good at that. But in special relativity, he wrote a completely correct form of special relativity. And along came his professor at the ETH, the school that he went to in Switzerland. And he developed a different way of expressing Einstein's theory of special relativity by saying that it is a fourth dimension. And he introduced a lot of fancy mathematics to show that you can think about time as being a fourth dimension, which has different properties than the three dimensions that we're used to. But Einstein said, "Oh, this is just useless simplification." But then he had to try to come up with a theory of general relativity. And for general relativity, he needed that concept of the fourth dimension. And he did not have the mathematical tools to deal with it. So he had to go to a mathematician and have him teach him enough about tensor theory, which was not often taught to physicists at that time, that he got the tools that he needed from a mathematician in order to make his successful transition from special to general relativity.
Yeah, interesting. That will also happen with Heisenberg, as we'll see next time. because Heisenberg will come up with some results and he doesn't know how to express them. And it's this tortured expression. And he does come up with a way of saying what he means. And it's all very convoluted. And somebody else looks at it and says, you know, I remember a mathematics teacher I had back in the day, and he had a kind of mathematics. I never really understood it very well, but then they looked back at this guy's mathematics and it turned out to be matrix mathematics. And then these matrices were doing exactly what Heisenberg was trying to do. They were able to keep different parts and correlate them all at the same time, right? And that is what Heisenberg was trying to do. So yeah, you're right, that mathematics, the relationship between mathematics and nature is mysterious. So what do we say? Yeah.
Shirley, go ahead.
Fred, I just love your expression, time and history. Do you feel like sometimes in history move very, very rapidly, and sometimes in history seem to just plug along and maybe building blocks are being made that time then speeds up? What are the movers of our time and history, and where are we now, do you think?
Well, that's tough. That's a tough one. But yeah, I think you're right. I think there are moments of creativity and bursts of creativity. And then there are other times when we are just plodding. We're kind of, as Kuhn would say, filling out the paradigm until it shifts again, right? I would say that certainly in the 17th century, that was a time of major innovation in thought for science.
It feels like things are moving very rapidly now in the scientific field and in the medical field.
Yeah, I don't know how that goes until because they seem to be building. Nobody's an expert here, at least I'm not, in summarizing this, but it seems to me that if you go to in physics at any rate, talk about the 17th century, then if you talk about the 19th century, you do have at the end of it this enormous period of where quantum theory comes in. And that changes the way we think completely, right? And we've been mopping up from that for a long time now. And I don't know people say, well, are we going to replace it? Well, that's the thing. People get so used to it, they think, well, we're getting near the end of science. And then something comes along and says, not so fast. And so I don't know what, if anything, is going to replace quantum theory or modify it in some fundamental way, but I wouldn't be shocked if it did. And this is where I think, personally now, that the debate is with respect to Darwin's theory. Yes, natural selection is definitely one of those building blocks. Whether it's going to be solely natural selection that explains how we've changed over time as living organisms, or whether we're going to modify that in some way and bring in, other factors that nobody is actually seeing yet about, and there are some debates about this right now out there, but people tend to become dogmatically entrenched in what they're used to. And the older generation, it always takes a younger generation to do this. When quantum theory came along, all the older generation says, you're ruining science. You're not going to be, we can't fund this kind of stuff. And it's the younger people that insist that you've got to go down this route. And that's why Jacob Bronowski once said that students must bring what he called their ragamuffin thinking into the realm. Theirs is not to worship truth, but to question it. And so we do have to remain open, no matter how much we are impressed by the achievements that a given, I'll use the word paradigm, has been able to put out there. So yes, these things go in fits and starts. Where we are in the fit and start right now would depend on the field to some extent, whether you're talking biologically or physically. And I think, well, personally, I have the feeling that we are becoming more and more aware of just how fundamentally integrated the sciences are with the arts. I think that's becoming more clear, that everything seems to be possible, even the most outlandish things. But that's always the challenge, because you can't go with every crackpot. Sometimes the difference between a crackpot and a genius is only available to you after the effect. So when it's over, you look back and say, well, that guy, he was crazy. But this guy was a genius. But before the fact, you still have to keep humility, at least in my view. So, well, we have gone beyond the hour, but.
I was going to ask if John wanted to make any final comments.
No, I don't think so, except to say that I've heard the history of relativity and quantum mechanics said several times, but I've never heard it said precisely the way Fred has done it. But I think he's done a wonderful job of giving it at a level where I think most of the people understand a little bit more than they did before. And so I thank you, Fred, for doing that.
My pleasure, for sure.
Well,
Thank you so very much. Hi, Julie. And I just wanted to thank Fred, too. It was unbelievably fascinating. When I heard you were a professor of history of science, I thought, what is going to happen? It was joyful and enlightening. Thank you so much.
Well, my pleasure, for sure. I've always enjoyed being with you people. So,
Thank you very much, Fred.
well then, till next time, when we're going to talk about another thing that wasn't possible that turned out to be possible.
Our next place in history, right?
Yeah. All right. I will
Thanks
leave
a
you.
lot, Fred.
Bye-bye.
Thanks, everyone. Stay well.